Hello everyone, sorry for the waiting. And my name is Shan Zhong. I come from the Swansea University, and my topic is about the deep learning stochastic reconstruction method with Hilbert curves. I think some people come yesterday are always almost familiar with the stochastic reconstruction method, which is wholly different from the many report reconstruction method today. So this method focuses on the porous material, and the porous material are very ubiquitous in nature, science, and engineering. Typical example including rocks, soil, concrete, cement, porous electrodes, and bone tissues, which consists of solid scattered matrix and pore space, allowing fluid to pass through or surround. And image-based reconstruction is a simple way to get vast amount of models, because in reality, it's always hard to get real high quality CT scanner images from the open source assessment or from CT. We may need to queue a long time for get a CT scanner. And the reconstruction method are usually classified as 2D to 2D, 3D to 3D, or 2D to 3D. This is a picture from the published paper from the previous research of our group. And we can see the reconstruction method used here is to slide a window to scan the whole porous material and construct the middle part of that. This is 2D and this 3D, and this is the example of that. For my problem is I want to find a method to flat 2D and 3D CT images to 1D vectors, then use these 1D vectors to construct input and predict pairs to make the reconstruction. And the problem now is how to flatten the 2D and 3D images. Here I find it here the curves. Maybe this is very popular in computer geographics, and this is the 2D Hilbert curve and the 3D example of Hilbert curve. The most advantage of this kind Hilbert curve is that it can preserve the local data well when flattened from 2D or 3D to 1D. We can make a compare here. The left picture is we can just find this yellow point as the target, and it has eight neighbor points. Now, and one is flattened to 1D. And he still has 4 neighbor points, which is near or very close to it. But if we just flatten the 2D image as the conventional method, like this snake curve or line by line, it can only get 2 neighbors, which is still near it. And this is only 8 times 8 picture, but when the resolution is high, this point will become far away from this yellow point. So, and for the construction of input and the predict and output, I just choose like this. The input is 13, 29, and 53. How to say? This is based on the traditional 2D or 3D slide window method. What I want is to keep all the information surround the yellow point, and this is 8 plus 8 pixels in the image here, and we can see it's still very small. But if we want to expand or have a longer expand this area, we need to a longer input here. And now I choose this technique. I encode 4 pixels to 1 pixel with different labels. We can say the 4 pixels have only 16 different conditions, so we can just label it from 0 to 15. And from the beginning, I just tried the simplest architecture of neural network, like this, and make a classification as the output as 0 or 1. And this is my result now. It's not very good, but I can say that it looks similar. It looks similar between the training data and the predicted data I got now. Yeah, this is this is what I got now. And for next step, I maybe try the new architecture of the neural network, like this convolutional neural network. Scan your different size of the kernel to get the different characters of the input data, and also use some multi-level this contrast method to smooth these pictures. We can say the picture has the edge between the white and black is not smooth, and some noise between this a white area. I can get some method to smooth this. Yeah, that's all. Thank you.